Hello, today we are going to study the air jet spinning, and we are almost come to the last row of this particular chart that we have seen earlier. We are going to see the wrapping process with fibers, which is classified under the spinning process group as air jet spinning. And this commercial or the company name is Murata MVS. This Murata name we have seen earlier under the row over here, Murata MJS, which is classified as a false twist process group. But this particular system is very much different from the system that we have seen earlier, which was a two nozzle air jet spinning. In this case, there is only a single nozzle. Similar to the Murata MVS, which is classified here, there was one more machine which was introduced by Reuters, known as J10 air jet spinning machine. And whatever fiber we get is a fiber wound yarn. We get a similar yarn to the earlier one, core twist free and wrapping fibers with twist. It is the yarn look or the appearance would be similar, but the production method is entirely, or the production principle is entirely different. And yarn strength is imparted by aerodynamic wrapping. So with this we begin with how the mechanism works. So before we go to the theory of this, let us have a look at the animation of this particular air jet system.
Air-jet spinning technology produces top-quality comfort jet yarns at high production speeds. The sliver is drafted through the 4/4 roller drafting system. Each spin unit is driven individually. The draft settings are set centrally from the machine control panel. Fibers that leave the drafting zone are guided through the fiber feeding element, FFE, by means of negative pressure. The FFE shape is designed in a way to keep the fibers controlled in the parallel position for entering into the spinning tip. The front part of the fibers enters the tube of the spinning tip and creates the core of the yarn. The four air jets in the twist element create a whirlwind around the spinning tip by means of pressured air. The air drifts the loose fiber ends around the spinning tip. With the spinning speed, the wrapped fiber ends are pulled inside the tube and they are twisted around the yarn core. The comfort jet yarn structure shows parallelized fiber mass forming the core of the yarn, and the fiber ends twisted around the core. The yarn surface is smooth and even, and shows a low value of yarn hairiness.
Okay, so with this, let us see the system and how it compares with the MJS. The MJS, which is the full form is Murata jet spinning. It was the two nozzle air jet spinning system that achieves a faceted yarn character. We have seen the kind of yarn that was produced, wherein a structure which was having a twistless core and the twisted surface fibers, and this particular yarn was produced by false twist during spinning. In the case of MJS, the false twist limits the surface fibers to only about 5%. We have seen that whatever the fibers that are there, the edge fibers that are created, only those fibers are able to wrap themselves around the core in case of an MJS, and the percentage that would wrap around would be only 5%. Therefore, it is successful for the processing of only of man-made fibers or its blends with cotton, but it was not very successful for 100% cotton, and that's why for 100% cotton the air jet yarns do not have sufficient strength. because using cotton fibers on this particular system would lead to weaker yarns, and therefore it was not found successful in case of 100% cotton fiber spinning. So we come to the new system, that is the MBS system, which is Murata vortex spinning. This system does not make use of false twist for yarn formation. After some time, as we saw, Ritter also launched its airjet machine J10 in 2008. Compared to the two nozzle airjet spinning based on the false twist principle, this system allows an increase in the number of surface fibers. That means earlier in case of MJS, we saw that only 5% fibers were there as the fibers that were on the surface, which would wrap the core fibers. This particular, as against that, MBS would allow around 15 to 30%, which would result in an increase in yarn strength, especially in case of cotton. So this particular system, the earlier disadvantage that cotton fibers could not be spun has been eliminated, and now we can even spin 100% cotton fibers very successfully on MVS spinning system. The new airjet system has therefore eliminated all the drawbacks of the earlier system. So with this, let us see the passage of material through the machine. So we have a sliver which is being fed here. There is a feeding roller. Then there is a middle roller, apron with apron rollers, and front roller. This is basically the drafting unit that we have seen in the animation also. Then there is a housing which has got the nozzle through which the fibers enter, and the yarn is actually made here. Then as soon as the yarn comes out of this nozzle, you will have a yarn quality sensor. Then there is a take-up roller and a yarn monitor, and also a waxing device. And just like a rotor, you would get a final package which wouldn't require a second winding stage. So between the drafting unit and the point of yarn formation at the entry to a stationary spindle, the fibers enter the spindle in an absolute parallel state. We have seen how the fibers enter. They all are almost parallel, and the spindle is of course stationary. Um, so coming to the next point here, during this fiber transport, a certain number of fiber ends are separated from the main fiber flow. So the image, it looked like this, that the fibers, some fibers, the core fibers would enter parallel, and there were some fibers which would be left out, and they are the ones which would wrap around the main core fibers. These fiber ends are then twisted around the non-rotating yarn core at the entry of the hollow spindle by the action of single air vortex. So there is a single air vortex that is there generated around this spindle here, and whatever fibers are left out, they would just wrap themselves around the core. This is the spindle, and this particular edge end is known as the spindle tip. So let us look at the air vortex a little bit in more detail. The fiber feed channel and the spindle are surrounded by a housing. We have seen that it's a casing. It's a in the image we saw earlier in the passage. It was a closed casing, and within that, the air vortex near the spindle entry generates a certain vacuum. It's a housing, and inside that the vacuum is generated, which results in an airflow through this particular channel. This airflow transports the fibers from the drafting unit to the spindle entry. In the earlier animation, we saw that the air enters through four different entry paths, and this airflow transports the fibers which comes out of the drafting unit right into the spindle entry area. By the action of the vortex, the fiber ends eventually whirl around the spindle tip and are thus twisted around the twistless yarn core. We have seen that the yarn core was twistless, and the fiber ends that were coming out or were left out were wrapping themselves and transformed into a twisted yarn surface or cover fibers. This occurs at the spindle tip. So having understood how this yarn is made, let us see wrapping process with fibers on a airjet spinning system. In order to make airjet spinning possible, two quite difficult tasks have to be solved in the zone between the drafting system and the entering the spindle. Between this zone, we have to see that the task, that is the separation of the free fiber ends, that is the first task, which is difficult enough to get this free fiber ends, which would help us in wrapping the core fibers. And the second main task would be prevention of false twist formation. So let us see how they are both tackled, or rather which are the factors that really influence both these factors. So let us understand first this parameter here, which is known as L. This L is the distance between the front roller nip from where the fibers are coming out and the spindle tip. This is the spindle tip. So between the nip and the spindle tip, whatever distance is there, that is known as L and is shown or marked here. So the separation of the free fiber ends depends on the correct choice of the distance L, which is the distance that we have just seen. So let us see a little bit in more detail how this L actually affects yarn properties, some other properties or some other parameters in the spinning of air-jet yarns. The distance L must be slightly lesser than the average length of the fiber being processed, enabling the transport air into the fiber feed channel to separate the fiber ends from the main fiber flow. So this particular statement tells us that this L, whatever distance is there, it should be slightly lesser than the average length of the fiber being processed. So when we keep this optimum distance between the front roller nip and the spindle tip, it helps the transport air in the fiber feed channel to separate the fiber ends from the main fiber flow. So this is the main factor which will provide us with the free fibers that are required for wrapping and making the yarn. So longer the distance, more will be the free fibers ends available for wrapping the core fibers. So we need to increase the distance if we feel that we require more fibers for wrapping. Lesser the distance, what would happen is there would it would lead to lesser free fibers, and therefore most of the fibers would be tightly assembled. That means the core would be tightly assembled because less free fibers are available, and this would eventually lead to lesser risk of losing control over the fibers, because once the fibers are free, then there is a big risk of losing control because the air vortex is acting in this area, and therefore if you have a lesser distance, there would be a lesser risk of losing control, and therefore the yarns that we would be producing would be more even, with fewer imperfections and lesser hairiness. The structure the structure that would be formed by keeping a lesser distance between of L would give us a yarn structure which would be similar to that produced by the MJS system of spinning, where we had earlier seen that only 5% of the fibers are acting as wrapping fibers. So similar kind of structure we would be able to see, because the moment we increase the, or rather decrease the distance L over here, there would be lesser fibers to be wrapped, and the structure would then start looking like that of the yarn made on MJS system. So there is a possibility, now the same distance we are talking about, there is a possibility of short fibers being extracted, and such fibers will not be part of the yarn. So in this particular vortex, there is another point that we need to consider, that the shorter the fibers that are being fed over here, those fibers, there is a risk that they might be just be eliminated due to suction, and it might not be able to form or rather make a yarn out of it. It would not be a part of the yarn. The percentage loss of such fibers, such short fibers, is around 5 to 10%, which is quite high, and therefore higher the short fiber content in the feed sliver, higher would be the fiber waste. So this is one thing which we should consider while preparing our sliver for feeding to the air-jet spinning system. We should take care that the short fiber content is low. So with this parameter that we have seen, the first parameter, that is L, today we come to the end of today's lecture. Thank you.